this is the 38th lecture of the course MTH 204A for section B. Recall that in the last lecture we have observed that for a finite group and a finite dimensional irreducible representation over C and any given class function. So, let me remind you that a class function is a function that is constant on every conjugacy class. So, then this operator is this scalar times identity. As I have said that this is going to be instrumental in the proof of the fact that the distinct irreducible characters are going to form an orthonormal basis of the subspace of class functions. So, as earlier let me first assume that Wi rho I from 1 up to k. So, up to isomorphism, these are all mutually non-isomorphic irreducible complex representations of the finite group G, which we have considered. And furthermore, let us also assume that the character of the representation rho I is chi I, and as I said, the claim is an orthonormal basis of the subspace of all class functions. Okay. All right. So, how we proved is this is an orthonormal set that we have already argued. Now, we have to show that this spans the whole of H, and the way we prove is it suffices to show that if F lies in the orthogonal complement of each of these chi i's, then f equal to 0. It's a constant 0 function, and which is again this is sure or equivalently f bar is 0. So, how is f bar defined given a function f from G to C? So, f bar is the function defined from G to C in this manner that f bar of G is nothing but the complex conjugate of f G for every G. Okay. So, it is clear that f is also 0 everywhere is same as saying f bar is 0 everywhere. So, we show that if f lies in the orthogonal complement, then f bar is going to be 0. That's enough for yeah. So, that's enough. Okay. So, in the last lecture we have gone through the first step of the proof. Let me just quickly recall that for you, or maybe for the sake of completion I can let me do the whole proof in this lecture as well, including the first step. So, the observation is the following, that the observation is as follows: if let us say some some u phi is if this is an irreducible representation. Of course, all the representations that we are going to talk about are always over C. Irreducible representation of G over C. Then we look at the corresponding operator f bar G phi G. Okay. We look at the corresponding operator, and what we have observed is thus is an irreducible is this is nothing but f inner product of f with so like we have already observed that, right. So this is going to be inner product of, so the way we do it is basically going to be the inner product of like how does it inner product come if we just take the trace of the left hand side. The trace of the left hand side is simply summation fg times the character of this. So therefore just if we assume that conjugate here, this becomes this some chi of phi, just simply the chi or the character of the representation phi, right. Now we have assumed that these are all the irreducible representations, all up to isomorphism, these are all mutually non-isomorphic irreducible representations. So therefore chi phi must be one of these chi i's, okay. So from the reducibility of phi, so it follows that, so this is nothing but for some I, it will be the inner product of f with chi I, and by our hypothesis that is going to be 0. So therefore this is going to be 0, okay. This is a 0 linear map. So that in the first step we proved that for any irreducible representation phi, if we consider this operator, then that is going to be the trivial operator. So this is for any irreducible representation. Now we shall extend that to any arbitrary finite dimensional representation. So the argument goes as follows, that now assume let us say assume V rho is any representation, V rho is a finite dimensional complex representation, not necessarily reducible, okay. Now using Marshke's theorem, you can write V as the direct sum of irreducible G invariant subspaces, or in other words the representation rho decomposes, the representation rho is isomorphic to the direct sum of some subrepresentations. So what we do is for each I in 1 up to L, let's denote the subrepresentation, of rho, subrepresentation of rho on ui by let's use phi I, okay. So therefore you see this the phi, therefore phi I is basically the representation of G on ui, defined as phi I of G is rho G restricted to ui applied on, yeah. So this is what we have for all G. Therefore, so then for corresponding to, then what we are going to show is this operator rho G, we would like to show this is also 0. So how to show that? So recall that if we apply this on n a vector V, so this vector V can be written as a linear combination, can be written as a sum of vectors of this form, and this decomposition is unique. So therefore what we can do is just an observation that shows that, so rho G of u1 ul, okay. So now what is rho G of u1? u1 is in u1, so rho G of u1 is nothing but phi 1 G of u1, right, because that is what because phi 1 is nothing but the restriction. So therefore this is what we can immediately see, that the whole thing just turns out to be the following. So f bar G, the first one is this phi 1 G of u1 phi so okay yeah, phi 1 G of u1, and that's how it goes. Okay. F bar G phi LG of UK. This is what we have for every V. Now, what about each of these summands? So, each of these linear maps. So, by your assumption, each UI is irreducible, right? Because that is how by Marshall's theorem we do have such a decomposition, and there hence this each phi I is irreducible. So, once we have an irreducible representation, our observation made in step 1 that confirms this is going to be 0. I mean we obtain that each summand in this sum is going to be 0. So, therefore, this is also 0. So, thus for every V we see that this operator is sending V to 0. So, therefore, this in particular shows this is the 0 operator. So, what we have observed in the first step, now we have extended that extends to any arbitrary finite dimensional complex representation in step 2. Okay. So, thus so far what we have obtained is, let me again say in quick say in one line that, so whatever irreducible, whatever representation, not necessarily irreducible, whatever representation we take, finite dimensional complex representation, we are going to get this operator is 0. Okay. Let me just erase and write that. So, for any representation this is 0. So, for any representation this is 0. This is 0. Hence, in particular one can take rho to be the left regular representation of G, and once that is there, then so f prime G R G of G, this is 0. So, therefore, if we let us say let fix take any x, let x be in G, if we apply that to Ex, that is going to be 0, right, because this operator vanishes identically there. Now, the reason for applying this operator on Ex is very, I mean it is easy to see, because for left regular representations we have done all these, that Rg of Rg of on any x is nothing but Egx, right. So, therefore, this simply implies that f bar G E times Gx, where G in G is 0. Okay. Since G runs over all, all elements in the group G and x is fixed. So, therefore, thus Egx, so Gx runs over all elements of G as well. So, therefore, what you see here is we thus obtain a linear combination of the basis elements. So, recall that this Ex, this is a basis of Cg, right. So, you obtain a linear combination of the basis of Cg which vanishes, therefore, that will force for every G in G, f bar G will be 0. That is exactly what we want. Okay. So, the steps of the proofs of the following, that it shows that it is enough to show a function that lies in the orthogonal complement of each of these chi i's, that has to vanish. So, showing this as vanishing everywhere is same as showing its complex conjugate vanishes everywhere, and the way is the crucial observation. The instrument, what is instrumental is this observation. So, first we show this operator is 0 whenever first we show the such an operator is 0 if I is irreducible, then we extended that to any finite dimensional representation. Therefore, that enables us to consider the left regular representation in particular, and therefore, the rest is just some simple linear algebra, which is basically the definition of a basis of a vector space. Okay. So, this establishes our theorem. So, as an immediate corollary, what we obtain is, so this observation again is going to be quite important for us later on, but anyway. So, what an immediate corollary? So, earlier we have seen that, earlier we have exhibited a basis of H, namely the indicator functions of the distinct conjugacy classes. So, that we have explicitly we have seen that. So, therefore, H has dimension equal to number of conjugacy classes in G, and here also we have proved that this forms an orthonormal basis of H. So, therefore, it follows that K has to be equal to the number of conjugacy classes. So, distinct number of mutually non-isomorphic irreducible complex representation number of mutually non-isomorphic irreducible complex representation of G is number of distinct conjugacy classes in G. Okay. As an immediate example, if you just for a simple example, if you just take G equal to S3, so in S3 you have identity, then 1 2 3, 1 3 2, and then 1 2, 1 3, and then 2 3, right. So, here you see that only 3 conjugacy classes. So, thus S3 has only 3 mutually non-isomorphic irreducible complex representation, and of course, if their dimensions are, for example, the first, in that list, of course, trivial representation has to be there, because trivial representation is on anyway it is irreducible. So, therefore, like if n1, n2, n3 are the dimensions of those 3 representations. So, let me remind you that by the dimension of a finite dimensional representation, I mean the dimension of the vector space on which we are considering the representation. So, if these 3's are the dimension of the irreducible representations of S3, then one must have n1 square, n2 square plus n3 square, okay, equal to 6. Now, what can you say here further? So, in that list, of course, you have the trivial representation. So, what is a trivial representation for any group G? Like you just simply let me again remind you that for any group G, the trivial representation is simply like it is a one dimensional representation. So, C minus 0, because one dimensional representations are same as saying homomorphisms from G to C minus 0. So, that is exactly given by sending each G to 1, okay, or and if you want to say it in the form of in the usual form. So, therefore, then it means that you are the representation is of G, it is on C, the represent the okay G to GL of C, and the corresponding to each G, the linear map rho G is sending each complex number to itself, okay. So, this is we have already talked about that. So, each group element acts trivially. So, therefore, one of these ni's will be 1. By relabeling, let me assume that this is 1, okay. And what else? if you remember that we do have another one dimensional representation of Sn, namely the sign character, because again one dimensional representations are same as their characters, because GL of C, the GL1 of C is nothing but C star. So having a homomorphism from G to GL1 of C is same as having a homomorphism from G to C star. So therefore we do, given any Sn, we do have the sign character. So that is, and sign character is of course different from this trivial representation, right, because sign character that takes with the value -1 some places, but whereas the trivial representation does not do that. So therefore sign representation or sign character is a representation, one dimensional representation, which is not isomorphic to the trivial one. So these are very elementary observations, because their characters are different, or yeah. So therefore here you have one more one dimensional. So this only forces that the third representation, irreducible representation, must be two dimensional. Okay, the third irreducible representation must be two dimensional. And furthermore, I would like to remind you that even this representation of S3, this irreducible representation, that also we have seen in one of the earlier lectures. So let me simply remind you of that. So what was that example? I think the irreducibility, you should, if you haven't checked already, you should do that. So let me simply say that the following, that S3 has two one dimensional representations two means two non-isomorphic. What are those two representations? Namely trivial representation and sign. Okay, sign representation that sends each even permutation to 1 and odd permutation to -1, and then S3 has one two dimensional. So one dimensional representations are by default already irreducible. One two dimensional irreducible representation. So all the representations here as usual over C. So what is the representation? So like inside C3 we consider the hyperplane given by, well, I should not use the same notation, is x, y, z in C3. Okay, so this is a hyperplane, let us call it P, and then automatically S3, since this is a two dimensional subspace, S3 has a representation. So basically that we have already discussed about this, that this is going to be a S3 invariant subspace of C3. So therefore S3, so therefore this, we consider the subrepresentation of S3 on P, and I think I have already given it as an exercise, or if you have not done that, then you can do it right now. This is just some exercise on linear algebra. So the exercise says this representation is irreducible. Okay, basically it is a two dimensional representation. If it is reducible, then there will be common eigenvectors. So that is what the problem is. The permutation matrices, they do not have enough common eigenvectors. Okay. All right. So we have just seen an immediate application of this. So this helps us. So this number, this observation together with the dimension formula helps us to get the all possible dimensions of the irreducible representations of a given group G when particularly the order is small. For example, this is one case where we do not have any other option. Alright, now let us deduce one more corollary of this, which is called second orthogonality. So yeah, so this is called another orthogonality relation. So what we do here is very simple. So like already we have proved that this chi I is chi 1 up to chi k. Now k is precisely the number of conjugacy classes. So this chi 1 to chi k is an orthonormal basis of our H, that is the space of all class functions. Now let's take let's denote the conjugacy classes are, let these be distinct conjugacy classes in G. Okay. So corresponding to each C for any I, we look at the indicator function of C of this conjugacy class Ci. Now that indicator function is, it has to be a linear combination of this chi i's because this is orthonormal basis. So let us write it as follows, that lambda 1 chi 1, lambda 2 chi 2, lambda k chi k. So each lambda I is a scalar, okay. And we also know how to, since this is an orthonormal basis, we know how to compute each lambda j. So each lambda j is nothing but inner product of with chi j, because we are dealing with an orthonormal basis. Now we can simply compute this inner product. This is not actually difficult. So this is why this is this times like so only the terms G, only the G's which lie in C1, they will survive, only those terms will survive corresponding to those G's which lie in Ci, only those terms will survive. And how many such thing you have? So this is basically the size of the conjugacy class divided by order of G. So yeah, divided by order of G. So what we do is like let's pick an xi from Ci, okay. So basically therefore you see that all those terms are basically the repetitions of chi g xi, okay, and the number of times that repeats is exactly the same as the size of the class chi g of xi, okay. And by orbit stabilizer theorem, this is nothing but like what is the size of the, so conjugacy class is an orbit, right? What is the size of the orbit? Size of orbit is G modulo the the stabilizer. So here the stabilizer is the centralizer. So therefore it is basically, I mean since yeah, this is the size of orbit. So this is 1 modulo centralizer of xi, right, because yeah, fine, because the thing is that for any x, this is the conjugacy class of x, okay, of this, okay. So that is how we have computed the scalars, right. So that is how we computed the scalars. Now we put that here in order to obtain the following, that okay, I should simply remove that and write. So, this is like this fellow, I should write using summations. So, for each I you can do that. So, okay, here it will be j from 1 up to k, j from 1 up to k, then this fellow, j from 1 up to k, then this fellow. Okay, so hopefully this quantity we can take out. So, yeah. So lambda k is going to be, so thus simply we will write the following, that Cg of xi times Cg of xi times this is, I mean this is what we are, this is actually the scalar xi times chi j, okay, and yeah, this is what we have, chi j x chi I, because again remember that this is what the scalar that we have just computed, 1 up to k, okay, good. So, yeah. So, this holds for whatsoever xi you choose from Ci, whichever xi you choose, that does not matter. This I mean then this is always going to be same, this is always going to be same, okay. So, for any choice of xi from the conjugacy class, this holds. So, this is what it has. Now, let us consider something else. Let us consider another element, let us say small g in capital G, then this, the above immediately says the following, this is times I think I have just made a very small mistake, this will be just this, yeah, because while you take inner product you have this complex conjugation in one of them. So, this is this. So, chi j of x. So, maybe I should write like this. That chi I g and chi j x I bar from j from 1 up to k, okay. So, therefore, what do you get here is the following from this is, if G lies in Ci, that is if G is conjugate to Xi, then this quantity is going to be 1. So, therefore, this product, this is going to be simply conjugacy class of G. So, therefore, conjugacy class. So, this is going to be simply the order of the simply this, if yeah. So, this is okay, I think I should yeah. So, maybe I should write like this. So, let us just write it, look at the sum. So, this sum is if G is conjugate to Xi, and otherwise certainly this is going to be 0. So, this product will be 0. So, this is the relations that we are having now. So, this product, so for any I, so for any I lying here, this product is going to be the size of the conjugacy class if this G lies in the conjugacy class of Xi, that is their G is conjugate to Xi, otherwise it is 0. So, this is called as this set of relations depending upon G lies or G does not lie, that is called that second orthogonality relations. So, the first orthogonality relations are which we have proved in this class, that which we have seen on the previously, that the distinct characters therefore they generate an orthonormal set, and now this is called the second orthogonality relations. Or some people call it column orthogonality relations. Let me explain why it is called a column orthogonality relation. So, it means that it has to do something with the columns of some matrix. That is exactly the point. Let us introduce the notion of a character table of a finite group. So, character table, already we are convinced that the characters of the irreducible representations, or character of the representations in general, they contain, I mean they contain, I mean they contain like very important information about that representation. They contain many very important significant information about that representation. So, in fact we have seen that we are like while dealing with the representation, while studying the representations, we therefore have to study, have to analyze their characters. So, the character table is the following, that suppose given a group G, we let these be our distinct conjugacy classes. So, given a group G, finite group, we denote these as the distinct conjugacy classes. Okay. So, from each conjugacy class we take a representative xk, and also we know that as we have done here, we have k number of irreducible characters. So, these are all distinct in the sense of mutually non-isomorphic irreducible characters. Now, what we do is we now consider a matrix. What is that matrix? So, basically in that matrix, or maybe another more appealing way to put that is the table. So, what we do is in the table, first let me give this put in this way, then we will formally say which matrix it is. In fact, it will be evident. So, in this matrix first here, and in this table first here, you write down the representatives that you have chosen. Okay. The choice of the representatives certainly do not matter, because each character is constant on each conjugacy class, and here you write down the characters. Okay, you write down the characters. Now, what you do is in the first row you evaluate the character at each of these points and you put their values. Okay, that is how you go on. So, therefore, the character table. So, given a group G, and first fix the, we have to first fix some ordering of the distinct conjugacy classes. At the next round, we have to choose representatives from each of those conjugacy classes, but again the choice of the representatives do not matter, because if I take some x3 prime from the same class, then chi1 of x3 prime is same as chi1 of x3. So, the order actually, to begin with, the order of the conjugacy classes that are going to, that is something on which the character table will be dependent upon, because then this whole, you see this, in this table the columns will be interchanged. So, given these, now the character table of G is the matrix chi I x j. Okay. So, this is the I 1 less or equal to I less or equal to j less or equal to k. Okay. So, given group G, the character table formally the character table is defined this as the, we say this is a character table of G. So, note that the character table that depends upon the order of the conjugacy classes, because the way you order then the columns will be changed. So, note it depends upon the order of CIs. Okay. But however, now we come to the explanation why the second orthogonality relations are called column orthogonality relations. So, that is actually quite evident from here. So, for example, if you take two distinct columns, let us say some ith column here and some jth column here, right. If that is the case, then just look at this. So, let me write it. Let me write it that so like what is this sum for when G equal to xi? Okay, so xi we just take so let's this into this okay, just a minute. J from 1 this. So, like when so here let's take I not equal to j, I not equal to j, then what do you get there is chi I xi chi j. I think I have made some mistake here in the very beginning. So, there must be some computational mistake here. Let me try to figure out. So, once we are doing that, yeah. So, what was the scalar? Scalar was the sorry. This was the case because this was the jth scalar that we have found out, right. This character times the central event. Again, let me repeat that. So, a lambda j was, yeah, actually here I have made a mistake. Lambda j was the inner product of this with the character xj, and that is exactly xj is xj, like for correspond to each of this I pick. So, this is x sorry. So, here xi lambda j of xi divided by the number of repetitions. So, the number, so therefore, all total we get the order of the centralizer of xi, yeah, yes. So, these are the scalars. So, therefore, I am sorry, this is what we are going to have, all right. So, now you see what the point that I want to make at this there is. So, xj, so taking j equal to xi, xj if we put small xj, okay, yeah, what are we doing here? Just to fine. This is not a problem. Xj, we are. Hey, hold on. I think I just want to make sure whether I have made any mistake further or not. No, it doesn't seem so. It's fine. Okay, so look at this. That whole same expression. X chi j g, where we take, so here where we take g as x j and of course on the other hand we have xi bar, yes, j from 1 up to k. Okay. We are taking this with g equal to, so we have fixed an I. Now take any other j, right, and take g equal to xj. So what is going to happen here? So xj is actually the representative of a different conjugacy class, so therefore this is going to be 0. So what is this actually? Isn't that the inner product of the, like if we view the ith column of this matrix and the jth column of this matrix, if we view these columns as the column vectors inside Ck, then like the ith column, so the ith column of, so let me write it in this way. So what is the ith column here? Chi1 xi, similarly chi kxi. Okay, this is the ith column. Similarly, you have the jth column. So if we regard this, both this inside Ck, then this is nothing but the inner product of these two vectors in Ck. So therefore this relation indeed implies that the columns of the character table, which is by definition of matrix, those columns are orthogonal to each other. So let me put it in this way, since we have observed this, columns of the character table form an orthogonal set of Ck. Okay. So simply columns are orthogonal, that is why we call this second orthogonality relations as the column orthogonality relations. Okay. But one more things here, we have just derived that the columns are orthogonal. From this, do not jump into the conclusion that I mean each column is orthonormal, these columns are also orthonormal. Don't jump into that conclusion, because that doesn't happen, because if you see that this is exactly the order of this. Okay. So if you take the inner product of a column with itself, certainly you are not going to get 1. So I mean the columns are, they are orthogonal but need not be orthonormal. Okay. So this is the reason for which we say this set of this orthogonality relations as the column orthogonality relations as well. So therefore we have, as I said, two sets of orthogonality relations for characters. One is the distinct characters, they form an orthogonal set. So which has, well, not exactly that's like for example chi I and chi j, they appear, their values appear as the rows of the character table. However, for all points in G we are not considering in this table, we are just taking representatives. So the earlier orthogonality relations, that has something to do with the rows of this matrix, but since the way we have defined the matrix, we cannot simply say that rows are orthogonal. Okay, that we cannot say, because we are not considering the values at every point. So but however at the most that you can say that the earlier orthogonality relations, I mean if you want to connect that with character table, so you can just say that this has something to do with the rows of the character table. But however, for the column ones, we exactly have that this is same as saying the columns are orthogonal. Alright, so since I have already talked about the character table, I should give one example, and in fact I will show that how sometimes, by a very easy example, namely that of S3, that how sometimes this column orthogonality relations helps us to find some missing entries from the character table. So the example that I am going to give, the stage is almost ready, namely the character table for S3. character table for S3 or of S3. So, what we have to do is, first we have to representative. So, this is identity, then a 3 cycle, then a 2 cycle, and by chi1 let us write down the trivial one. By chi2 let us denote the sign character, and by chi3 let this be the 2-dimensional character, okay, on the hyperplane. So, here it is just the chi1 of like chi1 is basically 1 for everyone, right. The character of so chi1 of anything is chi1 is the trivial character, no. Okay, so like here you see that the trivial character. So, for any ZG this is the identity, this is this identity map. Okay. So, what I am saying is, I think that it's quite clear that given the trivial character of any group, I mean we know its values, it's constantly it's 1. Now, for sign character this is even permutation, but this is odd, but this is also even, but this is odd. Okay. Now, for chi 3, at least chi 3 of identity will be the dimension of the representation, that is 2. Now, how to find these 2 missing entries, that we can do using the orthogonality relations of the columns 1 1 1 1. So, here you must have -1 and same 1. So, already you have 1 times 1. So, you already have 0. So, therefore, here you again must have 0. So, using the orthogonality relations sometimes we can find out the missing entries in the character table. Okay. So, enough of the orthogonality relations. Now, let me get into some let me get into again the decomposition of a representation. So, I will just briefly give you a sketch. Okay. So, let as usual G be a finite group, okay, and B rho be a representation of finite dimensional representation over C. Now, by Marshke's theorem we can have a decomposition of that into irreducible subspaces. So, namely U1, UK. So, the corresponding subrepresentations are always irreducible. Now, what may happen that the subrepresentation of some ui might be isomorphic to the subrepresentation on uj, though ui uj might be different, but however the subrepresentations might be isomorphic. So, what we should do here is we should collect, I mean among these the mutually isomorphic summands we may collect them together. So, let us assume that, I mean let me write it in this way, I1 up to Ik up to let us say I1 maybe N1, okay. So, I should do it this, let us say N1. So, these are the, so what I am saying is I can rearrange this direct sum into this way. Okay, I think the better way of indexing is as follows: 1, I mean U11 up to U1 N1, U21, U2 N2, or if you don't want N1, maybe we can say something else, L1, L2, U. So, yeah, U R1 because U R L R. Okay. So, this is the same. So, what we have done is we have clubbed the isomorphic subrepresentations together. So we assume that, so here the subrepresentation on uij and uij prime. So the subrepresentations, this subrepresentation uij, and so these are isomorphic, but however no subrepresentation from one group can be isomorphic to the subrepresentation from the other group, from the other cluster, you mean, if you are confused with the word group. So that we can do, that is a rearrangement of terms. So this is the, we have thus the separated out the mutually isomorphic ones, okay, mutually isomorphic ones. And then what we should do is, like here one thing it should be clear that this R, that is the number of such clusters, R cannot exceed K. So what is K? I will retain the previous notation throughout, and of course this is as well. So we have only, after isomorphism, only K number of distinct non-isomorphic representations. So R is less or equal to K. So all right, so what we can do is, let us denote this by V1, that denotes this direct sum by V2, VR, okay, VR. So like starting with any decomposition, this is what we can do. And remember that given any V, this decomposition is not unique. So in other words, I can employ 5 different people and give them the same representation to do this job. That first you decompose that into irreducible subrepresentations, and once the decomposition is done, you should club the isomorphic ones together like this, okay, and no communication is allowed between any two of you ever. So therefore once I ask different people to do this job, then it is likely that since like UIs are different, so therefore like it is likely to have that this VIs, this VJs, that they are also going to be different, because VIJs, they are nothing, they are made of this this UIJs. But actually this is not the case. We will show that whichever decomposition you start with of the given representation V, the VIs that we are going to get are going to be the same. So in other words, suppose as I said, I employ 5 people for that job, that the same representation is given to all of them and asked to decompose and then club together the mutually isomorphic representations. Then at the end of, once they are done, we see that the VIs, what they have obtained, these collections of subspaces VIs will be exactly same. So therefore, therefore this decomposition, we will show that this decomposition is it does not depend upon the choice of what you have started with. So this decomposition is called the canonical decomposition of the representation. Canonical means it's a very usual term in mathematics. It shows that canonical means you have something in a very unique way, and that does not depend on, it may start, people might have taken different paths at the beginning, but at the end they all arrive at the same place. So canonical decomposition. Canonical decomposition of the representation rho. Okay. This is what we will prove, that in fact we will show that each VI can be solely determined in terms of the character, in terms of this characters and the representation rho. But before that, let me try to explain the whole point. The whole point is the following, that the decomposition to irreducible subspaces, that decomposition is not unique. That is a very fine part of the finest decomposition, but one might have different ways to do that, and that will result in different subspaces. But once you club together the copies which are same, then what you are going to get I mean the way, I mean in your method the VIs that you are going to get through your method, that will be same as the same subspaces, of course orders might different in which they appear, same subspaces in, I mean same subspaces that the other person has thus obtained. Okay. So therefore for this decomposition it is canonical that you have some very natural and unique choice, okay, over which there is no on which there is no disagreement, because the disagreement might happen, the difference might happen because of the the different ways different paths one has taken. So in that sense disagreement might happen, but if you ensure that they all lead at the end at the same place, so therefore that what you obtain is something canonical and unique. So I mean you do have a very natural and a unique way. That is the, I mean usual sense in which the word canonical is used. Okay, so now I will show that whichever UI you should start, these VIs are unique. So this is called the canonical decomposition of this representation. So I mean maybe first I should give you a very simple example. So let us take the simplest group z modulo 2z, or multiplicatively which is isomorphic to the multiplicative group plus minus 1. Okay. So therefore and take V any representation of, let rho be any representation of this group. Okay. So therefore you see that rho 1 must be rho 1 must be this identity operator on V, and rho of minus 1 is an operator whose square is identity. Okay. This is an operator. Now from V we define V plus. V plus is the set of all V's in V such that rho minus 1 V is V, because the square is minus 1. So you have, so the minimal polynomial is x square minus 1. So it has eigenvalues x plus 1 and x minus 1. So you do have two eigenspaces V plus and V minus. Here you see our job is simple because this is identity operator. So even if it is there, I mean it is not going to create any trouble. So essentially we are just working with this single operator, and these are its eigenspaces. Eigenspaces are already invariant under the corresponding under this operator, and this is anyway not going to create any trouble. So therefore you see the canonical decomposition that we are looking for is basically this. It's basically this. Okay. Because so this is of course both V, not V plus, V positive, both V positive and V negative are invariant under the action of G. Okay. So this is a decomposition, and of course when I say that this is going to be the canonical decomposition, so that is required. I mean of course I have to establish that, which will follow from the general thing that I am going to do. Claim this is the canonical decomposition. So in that sense here you see the eigenspace decomposition is the canonical decomposition of the corresponding group, the eigenspace decomposition of the operator rho minus 1. This is the canonical decomposition of V. okay, of not V, of rho. Of course, as I said, I will establish why this is canonical, that will actually follow from this, but perhaps the important thing that you observe is here we have the, like, since this is the decomposition into direct sum, we do have projection maps. The decomposition maybe for today I do not have enough time, maybe tomorrow we will, I mean in the next lecture we will prove this canonical decomposition, but before that let me talk about this projection maps. So, given any V, what should be its projection onto this? So, isn't it the following, that V plus, let us say, rho minus 1 V by 2, what about this vector? If we call this V1, so this is all, this is by its very definition. So, rho minus 1 is identity. So, this is easily seen to be in V plus, okay. Maybe we should write a small plus here. Similarly, if you can immediately see, so that is the way you do that, decompose a function as a sum of even or odd functions, or a matrix as a sum of skew symmetric and skew symmetric matrix, same kind of thing is. So, like these are, and in this very simple situation, these are the usual tricks that you just apply by inspection. So, this is easily seen to be in V minus. So, therefore, that each V, so given any V in V, given any V in V, we write V as the, so okay. So, this part of course lies in V positive, this is in V negative. So, these are the projections of B on these two subspaces. The noteworthy point for which I wanted that this V, so V, the V plus is the, like, image of, the noteworthy point which will be useful for us. The noteworthy point is V plus is the image of this operator identity plus rho 1, right. V plus becomes the image of this. Similarly for V minus, right. So, that because that is how you are obtaining, and so this is, I mean, easy to see. So, this is the image of V plus is the image of this operator. The main point is that this V plus and V minus, V plus and V minus are, like, here they are, what are given to us? Given to us is the group and the representation row. You see this, both the V plus and V minus, they can be determined solely in terms of the group and the representation row, okay. So, given, like, namely the image of some operator that involves only the group elements and row. So, this is the crucial observation. So, a similar thing holds here. So, this is a crucial observation that will show that the, I mean, in general each Vi can be, each Vi is determined uniquely in terms of, each Vi, it can be determined solely in terms of the given representation row and the characters here. So, here what are the characters of this group plus minus 1. So, like, all the, both the characters are one dimensional characters, and so, like, one character is this one from G to C, the constant one, the other one is the opposite one. So, the other character sends 1 to 1, and so, and the second character is just sending 1 minus 1 to minus 1, okay. So, this is one character, this is another character. So, yeah, so here you see that, so 1 times rho minus 1, that is the first character, and here it will be image of half identity minus, so plus into minus rho minus 1, right. So, this is the second character. So, that is what like in the next lecture we show that each Vi is solely is determined solely in terms of the characters and the given representation that will establish the uniqueness. So, this is a simple example where through which we want to explain that what we are, I mean, in this example it is quite, this decomposition is very easy to obtain, and by means of this example we are going to, I mean, I am going to say that what I am going to do in the generality. Okay, in the next lecture we will finish the proof of the general decomposition, and with that I finish here.